So what are we going to do to locate inflection points? Nothing different. We do the exact same thing for determining intervals of concave up and concave down. So you find the first derivative, find the second derivative, determine where it's equal to 0 or undefined, draw your number line, determine your intervals, do your sign chart testing a point, draw your conclusions for your concavity, but now we just have one extra step, make sure the function is truly defined at that point. Then, if it changes concavity at that point, it is a point of inflection. So let's do a nice simple example here, really simple example here. If you were looking at the book, it says determine the points of inflection and discuss the concavity. So what we're looking for is intervals of concave up, concave down, and any possible inflection points. I do want to notice there are a couple different ways of writing inflection points here. They might just give you, in the book, they might just give you the x value where the inflection point occurs. But if we truly are looking for an inflection point being an ordered pair, we would need to find the y value. So let's just go ahead and do this test on here. So what's the first thing we do? First thing we do again is find that first derivative. Hopefully that's not too hard because this is a simple polynomial. The derivative of x to the fourth is 4x cubed, and the derivative of minus 4x cubed would be minus 4 times 3x squared, which is minus 12x squared. Again, we need to find the second derivative now. As much as it might be tempting to look at the first derivative, if we are doing concavity and inflection points, we are looking at the second derivative. So let's find the second derivative of this. Well, what's the derivative of 4x cubed? That would be 4 times 3x squared, which would be 12x squared. And what's the derivative of minus 12x squared? That would be minus 12 times 2x, which is a minus 24x. Again, we're going to set this equal to 0. This is a polynomial function, so it's never undefined, so we don't need to worry about that. So if we're setting it equal to 0, I'm going to go ahead and start factoring things. I realize that a 12x is in common on this. So if I factor out a 12x out of the first term, 12x squared divided by 12x would leave me with just an x. And if I look at the second term, minus 24x, if I divide that by 12x, I'd be left with simply a minus 2. So I have 12x times the quantity x minus 2 is equal to 0. I set each of those factors equal to 0. 12x equals 0 gives me x equals 0, dividing both sides by 12. X minus 2 equals 0, add 2 to both sides, and I get x equals 2. So these right here are called possible IPs. I told you on a previous page that we cannot call these critical numbers, we cannot call these critical values, because these are where the second derivative is equal to 0. Critical numbers and critical values are only where the first derivative equals 0. So these are not critical numbers, but we treat them just the same. So what do we do now is we create that number line. Create that number line. Let's think about that number line, okay? So I have my number line and I need to place these points. Here's the point 0, here's the point 2. That's what I care about, right? I'm looking at the second derivative, the value of the second derivative of those functions. At 0 it was 0, and at 2 it was also 0. I look at my intervals. The first interval would be negative infinity to 0. The second interval would be 0 to 2. And the third interval would be 2 to infinity. I move on to step 4. Now that I've determined my intervals, I need to determine the sign in each one of those intervals. So I'm going to plug this into the second derivative, and again, I'm going to always try to plug it into the factored version, 12x times x minus 2, because plugging it into the factored version is always easier, or almost always easier, I should say. Let's look at this. We need something between negative infinity and 0. How about negative 10? Any number between 0 and 2. How about the number 1? And any number between 2 and infinity. How about the number 10? Again, I just try to pick easy numbers to plug in. So I'm going to think about this. Plugging negative 10 into 12x would give me a negative value. And plugging negative 10 into x minus 2 would be a negative value as well. And a negative times a negative is a positive. So on that interval, from negative infinity to 0, I tested the number negative 10. It was positive, so every number that I plug in that interval must be positive. Let's look at the next interval from 0 to 2. I chose a test point of 1. Well, 12 times plugging it into the second derivative, 12 times 1 is a positive value. And then 1 minus 2, plugging it into x minus 2, 1 minus 2 is a negative value, and a positive times a negative is a negative. Because it was negative at our test point in that interval, it must be negative at every point in that interval. Let's look at when x equals 10. Again, I'm going to plug x equals 10 into these two factors. 12 times 10 is a positive number, and 10 minus 2 is also a positive number. A positive times a positive is positive. Because my test point in that interval was positive, every point in that interval must be positive. So what's that tell me? That allows me to move on to step 5, which is going to be about the original function. Again, anytime my second derivative is positive, my function has to be concave up. My second derivative negative means my function has to be concave down. Again, second derivative positive, my function is concave up. So I have now determined the intervals of concave up and concave down. Concave up was where my second derivative was positive, which was negative infinity to 0, and it was also 2 to infinity. So let's write those down now. Negative infinity to 0, and also 2 to infinity. Concave down are the intervals where my second derivative was negative. That was at the point 0 to 2. Okay. The last thing we have is inflection points. So how do we find inflection points? Well, inflection points are where concavity changes. Notice the second derivative changes sign, or the original function, the concavity, changes. So I notice when x equals 0, I do change from positive to negative, so that is an inflection point as long as it's in the domain of the original function. Number 2, again, I do change from negative to positive, so that is also an inflection point, because that is where it changes concavity, or the second derivative changes sign. As long as again, those points are in the original domain of the function. So what I need to do now is I need to plug those in to the original function, f of x equals x to the 4th minus 4x cubed. The two numbers that I'm plugging in are 0 and a 2. Well, I notice if I plug in 0 quickly, I would get the number 0. For 2, I'm going to go ahead and use my calculator. So I'm going to do 2 raised to the 4th minus 4 times 2 cubed. When I do that, I'm getting a value of negative 16. So what's that tell me? That tells me the point 0, 0 is an inflection point. And it also tells me the point 2, negative 16 is an inflection point. So there are my two inflection points. Again, those are inflection points because they are in the domain of the original function, and they change concavity, or the second derivative changes sign, at those points. So my inflection points would be 0, 0, and 2, negative 16. Hope that helps.